Hello and welcome to week 3 of Calculus 3. This week we are going to continue our discussion of vectors, but we are going to apply these vectors into the context of lines and planes in space. So the question that we start off with this week is, what is a line? A relatively simple question. When we started off in our study of functions in high school, linear functions were the first ones that we looked at. And in order to draw a line, we know that we need a point and a slope. So if I have a point and I know what my change in x and my change in y is, then I can define the line that would connect those 2 points. In 3 space, however, defining slope is going to be a bit more complicated. What is our rise and what is our run? Similar to the 2 space example, though, we still do have points. So I could start with some point and then try to find a slope. But again, what is the slope? In order to do that, we first need a point and a vector in the same direction as our line. So let's first suppose that we have a point. I'm going to call this point P0 of x0, y0, z0. This is our point. And from this point, we can go in many, many different directions. The direction in which I want my line to go can be oriented by a position vector. Let's call it v. Remember, a position vector is centered at the or has an initial point at the origin. So let's go ahead and call this vector v, which has coordinates a, b, and c. As is noted in the little gray box here at the bottom, we have a second point on our line, an arbitrary point, which we could label by, let's call it p, of just x, y, z. I don't know what the coordinates of this point are, but I do know that it is an arbitrary point on my line that is in the same direction as this vector v. Next, in order to set things up, we're going to look at a vector, because we're working with vectors, the vector that goes from the origin to my point P0. I'm going to label this vector as R0. I'll do the exact same thing for a vector for my point P. So here we're looking for a vector from the origin to my point P. And I'm just going to call this my vector R. Then I also have the line that is connecting P to P0. So that's going to be given by this line here, as best as I can draw it. So here is my line that is going through P and P0. The green line, the line that we are looking for the equation for, we know is parallel to the vector v by definition. And in this picture, we have quite a bit of vector arithmetic that we can do, and we'll look at that on the next slide. I've copied the image on the previous slide to this next slide to demonstrate what vector arithmetic we have here. Notice that the vector r, so our vector r is here, we can write as the sum of 2 vectors, r0, and this mystery vector here. So I'll go ahead and label and highlight this in purple. So we're looking for the vector here. So I've got this mystery vector that we're looking at. So I know that my vector r is going to be r0 plus whatever this vector is. Remember that we defined v as the vector, the position vector, in the same direction as our line. So I know that this vector is parallel to this vector v. However, it has a slightly different magnitude. The magnitude is altered by a scalar, and we're going to call that scalar t. So this vector here, again, is in the same direction as v with a different magnitude. So this vector here we can call t times v. Thus, we end up with our vector r being equal to r naught plus t times v. That scalar parameter is either going to make this vector longer or make the vector shorter, depending on where this second point P happens to be located. Because we defined our vector v as ABC, we can change the equation of r being equal to r naught plus tv in terms of components. R was given by x, y, z. R0 was given by x naught, y naught, z naught, and v by ABC, which then, after we do our vector addition, gives us that our vector r is equal to the following: x naught plus ta, y naught plus tb, z naught plus tc. Those components give us what is known as the parametric equations of a line. So what we're doing is we are taking a single point, P0, given by x naught, y naught, z naught, and saying, how do we change in x, how do we change in y, and how do we change in z? And that is given by that position vector v. From there, we can either scale from our initial point by v. We could scale a little bit longer. We could scale in the negative direction if we so desired. But we have a starting point and we have a way to move from that starting point to another point. And that's going to change for different values of t. For our first example, we want to find the parametric equations of the line passing through the 2 points given by 2, 3, 5 and -1, 5, -2. In order to do this, we need a point and we need a vector in the same direction as the line. We have two options for points, and now we need to find the direction of our line. We can do this by finding the position vector that corresponds to the vector that goes between these 2 points. In order to do that, we need to use our knowledge from even the first week defining vectors, that our vector v would be equal to, in its component form, we would have -1 minus 2. And then for the second, we could have 5 minus 3. And for the third coordinate, it would be -2 minus 5. This then simplifies to -3 to -7 as our position vector A, B, C in the same direction as the line. Now that we have that, we can set up our parametric equations. We know that the parametric equations are given by x equal to x naught plus at, y is going to be equal to y naught plus bt, and z is going to be equal to z naught plus ct. We have everything pre-set up. We could use, and we have a choice of what point we want to start with. In this case, I'm going to say let's set up 2, 3, 5 as our initial point. So my x naught will be 2, and then I'll have minus 3t. My y naught would be 3, and then I would have plus 2t. And lastly, my z naught would be 5, and I would have minus 7t. Be careful here, because there's not really just one answer to this problem. Notice that I could have switched the order of these, which would have ended up with a different vector in the end, negative of this vector v, so just in the opposite direction. Then I also could have chosen a different starting point. I could have chosen -1, 5, -2 as my vector as my point, my initial point, x naught, y naught, z naught. And so what I choose will actually end up with different parametric equations and different sliders. So just be careful when you're working through these problems that just because your answer isn't identical to the answer you see somewhere, that doesn't necessarily mean that you did it incorrectly. Just like we have two forms of lines in two dimensions, i.e. the slope-intercept form and the point-slope form, we have different forms of the equations for lines in 3 dimensions. The first that we saw were the parametric equations, and the next is what we call the symmetric equations. If we rearrange each one of the parametric equations to solve for the parameter t, so again here, this t is representing how far we have scaled from our initial point. So depending on how far you want to get away from that initial point or how close you want to be to that initial point. So how far we have scaled away from the initial point. And that scaling is going to be consistent in the x, y, and z directions. It will change depending on what the change in x, y, or z would be. So once we do that, we have t being equal to these expressions. And so we have that t is equal to x minus x naught over a equal to y minus y naught over b equal to z minus z naught over c. And as I mentioned, these are what we call the symmetric equations of the line L. In this example, we are just finding the equations, the symmetric equations of a line which contains 3, 1, 2 as a point and is parallel to the vector -1, 6, 2. So we can identify that 3, 1, 2 is going to be our x naught, y naught, z naught. And we know that the vector -1, 6, 2 is going to be our vector A, B, C, which is giving direction. From here, we can just plug in our values into the symmetric equations so that we have that the symmetric equations are going to be, we would have x minus our x naught, so x over 3 over -1, equal to y minus 1 over 6 equal to z minus 2 over 2. These are the symmetric equations of this particular line. The next part of the question asks us to find the point at which the line passes through the plane z equal to 1. So suppose that this pencil represents my line. Obviously, it's not really long enough to help us here, but imagine that this is my line. It has some kind of slope, and we could imagine that this plane is equal to, this piece of paper could be my plane z equal to 1. So if this is my plane z equal to 1, and I want to find out where this line intersects, I want to know for what value of x and y do we have when z is equal to 1. So all we need to do is set z equal to 1 in these symmetric equations. So if we have z equal to 1, this is going to mean that I have that x minus 3 over -1 equals y minus 1 over 6, which is going to be equal to, my z is equal to 1, so I would end up getting -1/2. I have two variables to solve for, but I know that these symmetric equations give me two cases. The first case is that I have x minus 3 being equal to +1/2 because of that -1 on the bottom. And the second is that I have y minus 1 over 6 being equal to negative 1/2. Solving both of these equations, we will end up getting that x is going to be equal to 3.5. And similarly, we can solve for y and say that y is equal to negative 2. So the line will pass through the point 3.5, negative 2, 1 on the plane z equal to 1. Here we have some definitions about lines in 3-space. The first two are familiar, and we've used them in 2-space. The notion of two lines intersecting if they have a single point in common. Two lines are parallel if they are in the same direction. And two lines are skew. This is a notion that we don't have in 2-space if they do not intersect and they are not parallel. So this notion here is unique to 3D space. We don't have this in 2-dimensional space where we draw two lines and either they eventually intersect or they will always be parallel. Skew lines are slightly more difficult to imagine, but you can easily use some manipulatives in your house to work through this. So two lines could intersect each other. We could have them be parallel. They're going to be in the same direction. And thus we could imagine sticking a piece of paper through those two lines, regardless of where they are in space. And finally, two lines would be skew if they do not intersect and are not parallel. So in this example, you could see that this line would continue on in this direction. This line would continue this way. They would never intersect. Think about two planes flying in space that never intersect each other. In this example, we want to determine whether the lines given by these parametric equations are intersecting, parallel, or skew. It's relatively straightforward to notice that these lines are definitely not parallel. Why? We can look at the direction vector. So if we look at the direction vectors, these are the vectors, our A, B, C, that give us which way our lines are going. So our direction vectors are going to be, in the case of the first one, V1. I can look at my parametric equations and realize here I have 1, negative 2, and 1. So my vector would be 1, negative 2, and 1. And my second position vector would be V2 being equal to, in the same way, I have that I would have 1, negative 4, and 3. So 1, negative 4, and 3. Remember that two vectors are in the same direction or parallel if they are scalar multiples of each other. And unfortunately, V1 and V2 are definitely not scalar multiples of each other. While things looked okay to get from 1 to negative 2 versus 1 and negative 4, it's not going to work. We can't multiply V1 by a number to get this. There's no way to do it. So because V1 is not parallel to V2, we know that the lines are in different directions. So because we know that the lines are in different directions, this means that those lines are either going to be skew or they are going to intersect. As I mentioned, this implies that our lines R1 and R2 are either going to be skew or they are going to be intersecting. The question now is, which one is it? In order to do this, we're going to assume that they intersect. So that's how we're going to start this off. We're going to assume they intersect. And from here, we're going to have to do quite a bit of algebra in order to finish up this problem. If these two lines are intersecting, that means that eventually my components are going to be the same. So I'll be able to find a T1 and a T2 so that these two components are the same. I would find a T1 and a T2 so that these components are the same. And for that same T1 and T2, my Z components would have to be the same. And we can write that down. So assume they intersect. That means that there are values of T1 and T2 so that the components of each are equal. So I would have that 3 plus T1 equals 5 plus T2. I would have that 3 minus 2T1 would be equal to 1 minus 4T2. And finally, I would have that 1 plus T1 would be equal to 1 plus 3T2. If these two intersected, I would be able to have the components all be the same. The third equation actually gives us a nice relationship between T1 and T2 if these two lines intersected. And it will yield that my T1 is actually equal to 3T2 because I see that those ones would cancel out. This equation is one that I can now substitute into my other equations. We need to substitute the equation given by star into the other two. So subbing in star, what we end up getting is 3 plus 3T2 being equal to 5 plus T2. So I'm down to a single variable. And in the other equation, I will get 3 minus 6T2 equal to 1 minus 4T2. And if we solve both of these equations, for the first one, I get T2 equal to 1. And in the second, I get T2 equal to 1. So thankfully, I got the same value for T2. Just like I said at the beginning, if these two lines intersected, there would be values of T1 and T2 so that all of the components were equal by coordinate. So the x coordinate equal to the x coordinate, y equal to y, and z equal to z for the same values of T1 and T2. Because I got T2 on both of these, I know that these lines are going to intersect. So we know that my T2 is going to be equal to 1, and we can substitute 1 into this equation, and so I would have that my T1 would be equal to 3. Now that I have those as my parameters T2 and T1, this means that my point of intersection, I can plug in these parameters into one of my lines, and it's going to be equal to, if I substitute in 1 into this equation, I am going to, substitute in my T1 into this equation, I would get 3 plus 3, so I would have 6. I would have 3 minus 6, so that would give me a negative 3. And finally, I would have 1 plus 3, which would give me that final coordinate point of 4. Lines were the simplest function that we could draw in three-dimensional space. The next simplest is the notion of a plane, though it requires a little bit more setup. However, it's similar to what we started off with in the idea of a line. The issue is that that direction happens in many different ways. So just like we started off our study of a line, we need to start off with a point. So in this image, just because this is going to be a way better drawing than I can do, I've copied this from the textbook. So we're going to start off with that initial point P0 being x0, y0, z0. And from that point, we can go in many different directions. I could travel this way, I could travel that way. And so trying to define a single direction on the plane isn't going to help that much. Instead, we'll look at, let's go in some direction. And that some direction is going to be to my point, P, X, Y, Z. Just like we defined the line, then we say, okay, I've got that R0 and R in the same way so that I could think about the line that would connect those 2 points. But because I have a plane, I need something a bit more. And the vector that is going to completely describe the direction of the plane is what we call the normal vector to the surface of the plane. The normal vector is always going to be perpendicular to the plane. So if we consider this vector, I know that my normal vector is going to be perpendicular to that vector. In fact, even if I chose another point, let's call that other point P2, and I looked at this distance, again, I would have a 90-degree angle between that line and my vector n. The vector n will be perpendicular to any vector on the plane in this image. As such, if I take the dot product of the vector n with any other vector on the surface, I should get a dot product of 0. Because remember, two orthogonal vectors will always have a dot product of 0. So if we look at this image, I define my R0 as the vector from the origin to the point P0. I define R as the vector from 0 to my arbitrary point on the plane. Then by vector addition, my vector R is going to be equal to R naught plus R minus R naught. And so my R minus R naught vector that is on top of my plane will be perpendicular to my vector n, thus giving me that R minus R naught dotted with my normal vector n should be equal to 0. This is known as the vector equation of a plane in 3 space. From the vector equation, we can generate the scalar equation. So suppose that we have n as ABC, that's my normal vector to the plane. I also have my R naught, my point being x naught, y naught, z naught, and my R to my arbitrary point just being x, y, z. Then I can note that I have R minus R naught by my vector equation dotted with my vector n is equal to 0, but I also know that I can do this out in its component form. R minus R naught is going to be equal to x minus x naught, comma, y minus y naught, comma, z minus z naught, dotted with the vector a, b, c. Using the definition of the dot product, this expands into a times x minus x naught plus b times y minus y naught plus c times z minus z naught. So we have a different equation, that being the scalar equation of the plane through a point with the normal vector n, and it is given by the following equation. You might also see a different form of this equation with a subtle constant difference. So if I wanted to rewrite it, I could expand it out and say ax minus ax0 plus by plus b, and I guess that'll be a minus, sorry, minus a by0 plus CZ minus CZ0. I could then have AX plus BY plus CZ equal to, I have and can move all of these terms, which are constants, over to the other side of the equation. But since they're constants, some people gather it into a single constant and call it D. Either one of these can be used as the scalar equations. This is just an alternative form that you may see in your work, and one that I wanted to throw out there now rather than later. In this example, we are starting off with 3 points, which are always going to define a plane. 2 points always define a line. 3 points will always define a plane. Let's see how that works. To save some time, I've gone ahead and plotted the 3 points in question into the 3-dimensional coordinate axes to give us an idea of what we have. As you can see, if you connect these lines, what we end up with is a triangle or a plane in this 3-dimensional space. And so what we need to determine is what the equation of the plane is, and what we need for that is an initial point and a normal vector. Remember, the normal vector is going to be perpendicular to any vector on the plane. What do you think would be some good candidates for vectors on the plane? Pause the video and think about that for a second. Because this triangle essentially defines the plane, any of the edges, when I think of them as vectors, would be vectors on the plane. So we could look at the vector that connects P1 to P3. So we could call this P1, P3. And we could also look at the vector that connects P1 to P2. Try to make that look a little bit nicer here. So the vector that connects P1 to P2, that is another vector. The normal vector n, wherever it may be, we know is going to be perpendicular to both P1, P2 and P1, P3. Let's write that down. So the normal vector must be perpendicular to both, this is the key word, to both P1, P2 as a vector and P1, P3 as a vector. Now, when you think perpendicular orthogonal to both two vectors, what do we think of? If you said the cross product, you are perfectly right. So in order to find the cross product, we need the vectors P1, P2, and P1, P3, which I'm going to relabel as V and W, just so that I don't have to write as much stuff. So my vector V is going to be equal to, I can find out what this is. I have my terminal point, so I have 3 minus 1, comma 0 minus a negative 1, and then 0 minus a 2. So my vector V would be given by 2, 1, negative 2. And then my vector W, same idea, terminal minus initial. So my terminal for P3 is going to be 4, and then minus 1, comma 2, minus a negative 1, comma 1 minus a 2. And so that will simplify into 3, 3, negative 1 as my vector W. So again, the vector, the normal vector, is going to be perpendicular to both of those vectors, and that will be given by n being equal to the cross product of V with W. So we have to go back to our knowledge of the cross product. So that is going to be, we'll have our setup in terms of I, J, and K. I'll go ahead, have you finish this up, and I will have it done by the time that you pause, finish, and then restart the video. After completing the cross product, you should have ended up getting 5i minus 4j plus 3k. Note that at the beginning, I made a slight typo and forgot that that negative needs to sit there in front of our j component in the cross product, but a slight fix of that and computing these determinants gives us this as our normal vector. Now that we have the normal vector, we can get the scalar equation of the plane given a particular point. Once again, note that the scalar equation of the plane is not going to be unique because we have multiple choices for what we could choose our point to be. I'll choose this first point as our x naught, y naught, z naught, so that my scalar equation of the plane will be 0 equal to my component of my normal vector, so 5 times x minus 1, my first coordinate of the point, and then I'll have minus 4 times y plus 1, and then lastly I will have 3 times I'll have z minus 2. So that is what is the equation of my plane that contains these 3 points. Just as we discussed lines intersecting in 3 space, we can talk about planes intersecting in 3 space. So if 2 planes happen to be parallel, those planes are never going to intersect. If they intersect, however, the point of intersection is not a point, it's actually a line. And so when we're trying to find the line of intersection between 2 planes, the work that we have to do is going to be slightly more complicated, and it's a little bit harder to conceptualize and draw. I've done my best to draw an image of essentially what the intersection of 2 planes looks like, as well as helping us set up for the solving part of this problem. First off, we can notice that these 2 planes are not parallel. So I'm going to label this first plane as P1 and my second plane as P2. Pause the video and think to yourself for a moment why we know that these 2 planes are not parallel. So we can establish what the normal vectors of these planes are based on the coefficients that the variables are being multiplied by. So these equations look more similar to that second form of the scalar equation, where we could identify the a, b, and c in front of x, y, and z, respectively. So we have that P1 has a normal vector given by 1, -2, 1, and P2 has a normal vector of 3, 1, -1. And so because these 2 normal vectors are not scalar multiples of each other, we know that P1 and P2 are not parallel. So this means, so because N1 is not equal to K times N2, this means that P1 and P2 are not parallel. And this helps us out a little bit in terms of our setup. In this image, notice that the line of intersection is on both the planes P1 and P2. So the normal vector is perpendicular, N1 will be perpendicular to this line, and the line will also be perpendicular to my vector N2. So this allows me to write down that N1 and N2 are both, keyword here again, both perpendicular or orthogonal to our line L. And now that we have this piece of information, we can use our understanding of the cross product. Our line L is perpendicular to both of those vectors, so its direction will be perpendicular to both n1 and n2. So we could use the cross product that the direction of our vector or our line L, so where V is the direction of the line L, is going to be equal to n1 crossed with n2. This is a computation that we've done a bunch of times before, so I'm going to leave that to you to work out on your own. But trust me when I say that the cross product, if we do it, will be I plus 4j plus 7k. So this vector v is representing the direction of the line. We know what the direction of the line is. Now we need a point on the line. To find a point on the line, we could just choose a particular value for z, because eventually, regardless of how not steep or steep the line is, eventually it will pass through when z is equal to 0. And this will help us set up what the line's, a point on the line is. So if z is equal to 0, we end up with the equations x minus 2y equal to -1 from our first plane, and we will also have that 3x plus y equals 4. Simultaneously, these must be equal because it's where those planes are intersecting. So we have a system of equations that we need to solve algebraically. In order for these two equations to happen simultaneously, it means that we need to solve a system of equations to solve for the x and y coordinates that happen when these two planes intersect at z equal to 0. So we can move things around slightly, and we will have that x is going to be equal to -1 plus 2y. And if I sub this into my second equation, I will have 3 times -1 plus 2y plus y equal to 4. And once we solve for y, this will give me that my y is equal to 1. And once I substitute back y equal to 1 into this equation, that will end up giving me that my x is also going to be equal to 1. By assuming that z is equal to 0 and looking at our two planes simultaneously, we found that a point that was on both of these planes and had the coordinate 0 for the z coordinate let us know that after solving this equation and getting y equal to 1 and x equal to 1, this let us know that the point given by 1, 1, 0 is on the line. So now that I have a point and I have the direction of the line, we can set up the symmetric equations. So writing this down, we have that the symmetric equations, we could go ahead and do the parametric equations if we wanted, but the symmetric equations of the line of intersection, and I'll abbreviate that, will be given by, so we know that it's going to be x minus a point that's on the line. So we will have x minus 1 over the x direction, which in our case is 1, equal to y minus the y coordinate over the, the y coordinate in that case will be 1, given by this, all divided by the direction in y, which is 4, equal to z minus the z coordinate which would be 0, divided by the direction of the z, which would be 7. So that gives us our final answer of x minus 1 over 1 equal to y minus 1 over 4 equal to z over 7. There is the second part of this problem that I've stated here, which is to find the angle between the two planes, but I've run out of room to do this. However, it's not all that bad to finish up. I've gone ahead and made a separate board to try to label this out. So the angle between these two vectors would be this angle, call it theta. In order to find theta, all we need to do is compare the normal vectors. Remember from our previous work that we had that the angle between two vectors would be given by cosine of theta equal to v dotted with w divided by the magnitude of v times the magnitude of w. This was the equation that we looked at last week when we were starting to talk about the dot product. In the case of two planes, the angle that's between them can be defined by those normal vectors. And so we would have that cosine of theta would be equal to n1 dotted with n2 divided by the magnitude of n1 and the magnitude of n2. Since we know the values of the component vectors for n1 and n2, we could go ahead and solve for theta. So we would have that cosine of theta would be equal to, my n1 was equal to, I had 1, negative 2, 1, and I would want to dot that with my other normal vector, which was 3, 1, negative 1. And then I'm going to divide that by the magnitudes of each of these vectors. So divided by the magnitude of n1 times the magnitude of n2. I'll leave you to finish up this computation. We've talked about distances from a point to a point, but what about distances from a point to a plane? There are actually a bunch of different distances that we could define, but let's suppose that to start off, we have a point, call it x naught, y naught, z naught, as we usually start with. Then the distance down to the plane is just going to be the vertical distance onto this plane. So let's call this distance d. If I have a second point on the plane, let's call that point x1, y1, z1. I also have the normal vector that comes from that point. So I have my normal vector n, which is equal to a, b, c. Now I have a vector that I can call v that's going to go from x1, y1, z1 until x0, y0, z0. Let's call that vector v. From v, I can project v and look at the shadow, and in this case, a long shadow, onto the vector n. So what happens there is if I take that green vector and project it onto the vector n, I end up with this right-sided triangle, and I can see that the distance here is equal to the distance here. So while this is a vector projection, since we're talking about lengths, thinking about scalar projections is actually going to be more helpful. So what we can see is that my distance d is going to be equal to the absolute value of the component scalar projection of the vector v, onto the normal vector n. So that's what our distance d is going to be. So again, here, this whole distance, and just to label it, that is the scalar projection of V onto the vector n. Now, using what we learned last week with scalar and vector projections, we know that the scalar projection of V onto n is going to be given by n dotted with our vector V, all divided by the magnitude of our vector n. Notice again that we're talking about the absolute value of the dot product because we want this to be a positive value, a distance. Then we can write this out. So I know that my vector V, I can write it. So here I have A, B, C. I'm going to fix that. There we go. A, B, C dotted with my vector V. I could solve and show that that is going to be equal to x0 minus x1, y0 minus y1, and z0 minus z1. Then I have that the denominator is going to be the magnitude of my normal vector n, which is the square root of a squared plus b squared plus c squared. From here, we can use the definition of the dot product so that this simplifies to, and remembering I've got those absolute value bars upstairs, I have the absolute value of a times x0 minus x1 plus b times y0 minus y1 plus c times z0 minus z1, all divided by the square root of a squared plus b squared plus c squared. We can then reorganize the equation here to separate out stuff that has to do with the plane and stuff that has to do with the point. So if we do that, on the top we get x0 times a plus by0 plus cz0 minus, we'll have a x1 plus by1 plus cz1, all in absolute value bars, divided by, and that's a horribly not straight line, there we go, square root of a squared plus b squared plus c squared. So here, we're going to fast forward to the definition that says if I have a point x0, y0, z0, and a plane given by this equation, then the distance is this. I have the beginning expression, but the question now is why is that d apparently equal to this? Well, remember that x1, y1, z1 is on the plane. So because it's on the plane, I can replace x, y, and z with x1, y1, z1. So then I would have, just to, and I'll erase this in a second, x1, y1, z1 equal to then a negative d if I move this over to the other side. So then all of this becomes equal to a negative d. And so we end up with the expression of the distance as this. If I gave you a point and a plane, we would just need to plug and chug those values into the formula for the distance between the point and a plane. In this case, we're given two planes and asked to find the distance between them. Now we can notice first off, if I label this first plane as P1 and I label this second plane as P2, we can look at the normal vectors of these planes. We would have that P1 has a normal vector given by, we'll call it n1. And using what we know about the coefficients and equations of planes, n1 is going to be 2, 3, -1. And P2 would have a normal vector. We can do the exact same process, n2, which is going to be equal to, we look at the coefficients, we see 2, 3, -1. So in this case, we have that P1 and P2 are parallel. So because they are parallel, we can imagine those two planes being in space, and the distance between them is always going to be constant. Versus if the planes intersected at some line, the distance between them would be changing. So to find the distance between these two planes, we first of all need a point on one of the planes. So any point that I choose, whether I choose a point up here or a point down here, the distance will always be the same. So the question is that we need a point on one of the planes. Doesn't matter which plane we choose, as long as the point we choose is on a different plane than the plane that we choose. To choose a point, let's start with our plane 1. So on our plane number 1, if we choose x equal to y equal to 0, eventually on this plane, x and y will be equal to 0. Then we have that our z is going to be equal to 3. We plug in 0, 0, so we get negative z equal to 3. So that just means that z is equal to -3. So we know that the point 0, 0, -3 is on our plane 1. Now that I have my point, I can apply the distance formula. Remember that the distance between a point and a plane is given by the absolute value of ax0 plus by0 plus cz0 plus d divided by the square root of a squared plus b squared plus c squared, where a, b, and c are the components of the normal vector, and we have that x naught, y naught, z naught is the point we're considering. So plugging everything in, we know that x naught, y naught, and z naught are going to be given by 0, 0, and 3. We know that our normal vector on P2 is 2, 3, -1. So we have 2 and then plus 3 plus a -1 times -3. So here we should say -3. And then in the denominator, we have the magnitude of the normal vector, which is going to be 4 plus 9 plus 1. And after a little bit of arithmetic, this will all simplify down to 1 over the square root of 14 as the distance between these two planes.